There are times when the inevitable end of life as we know it becomes the greatest mystery of all. And even for a star, old age involves many changes.
Stars, those faint points of light that we see in our nighttime sky, are actually great globes of glowing gas. Kind of sounds like an oath. But in any case, these huge hot spheres of gas, with temperatures of tens of millions of degrees in their cores, are gigantic natural thermonuclear reactors, which through fusion are able to shine and so balance against the force of gravity that's constantly pulling inward. The same gravity, in fact, which first prompted the stars to condense out of the diffuse clouds of interstellar gas and dust. And as the stars convert hydrogen into helium through this process, they remain in the main sequence phase of their lives. This is a very stable period, stable in size and in brightness. But stars don't last forever. They're consuming their own material in a constant battle against gravity, which they must eventually lose because they run out of fuel. And so they must change. And there are several different ways that once a star runs out of fuel, it can leave the main sequence part of its life, and the exact course it takes depends upon the mass of the star. But today we're going to be considering stars that are not so massive, stars like the sun. And this isn't very pleasant, but the sun will eventually run low on fuel. And when this happens, it will swell into a gigantic red giant star, the largest of all the stars. And in fact, the sun will be 1,000 times larger than it is now. Well, these red giants are seen elsewhere because other stars have gone through this process. And these objects then are the most conspicuous indicators of old age among the stars that we can see.
Most stars can be arranged by their surface temperature and intrinsic brightness into a continuous series called the main sequence. The bright blue giants lie at one end of the sequence, the dim red dwarfs at the other. Off this main sequence, there are some enormous red giants, and as their color indicates, these are cool stars. They may have started as bright blue stars, and in an evolutionary process of aging, their surfaces cooled and they eventually swelled to their enormous sizes. Most stars shine with a constant brightness because there is a balance between the force of gravitation that acts to contract the star and an elastic or pressure force that acts to expand it.
The main sequence phase of stellar evolution is the longest and most quiet phase. The star is converting hydrogen into helium, and the thermal energy produced in this way maintains the balance against the gravitational contraction. Now, hydrogen is a very efficient fuel, and also the star has a tremendous storage of hydrogen. However, only about 15% of its hydrogen can be actually used in this way because the condition is that it can be converted only in very hot regions near the star center. So after a definite time, all hydrogen must be exhausted, and that is the end of the main sequence phase.
An HR diagram can be used to illustrate the evolution of a star like our sun. Having first formed as a young proto-sun and then lived out its lengthy main sequence existence, internal changes begin to transform the sun into a red giant. For a time, the surface of the sun will boil from hydrogen burning and will increase in brightness. But as the chemical composition changes from hydrogen to helium and the nuclear fires begin to fade, the core will collapse. In response, the outer diameter increases and the surface temperature decreases. 80 million years after leaving the main sequence, the sun will change violently and expand 200 times, engulfing Mercury, Venus, and Earth. The helium will finally ignite in what astronomers call a helium flash. With the change of fuel, strange things may happen. Like more massive stars, the sun could become unstable. It could pulsate and be known as a variable star. There are many other types of variables. Some pulsate once a year, others in a few seconds. Once past the variable stage, the sun will become brighter still, 10,000 times brighter than our present sun, and expand 300 times larger. It will have reached its maximum size, becoming a red giant.
When stars evolve across the HR diagram, they pass through a region known as the instability strip. In this region, the envelope of the star is pulsationally unstable, and the star will physically pulsate, change in size. When it does this, its luminosity, at least the luminosity in the visible region, will change in a very regular manner. A classical example of this type of star is the Cepheid variable. These stars have proved very useful in astronomy. In stellar evolution, we can look at the period, the luminosity of the star, and from this information we can get a handhold on what the exact helium and metal composition of this star is, and also gain some knowledge of what the current mass of the star is. In regions other than stellar evolution, the Cepheid variables have proven extremely useful as a standard candle. It's been discovered that there's a very precise period luminosity relation, such that a longer period star has a higher luminosity. So when we look at one of these stars, we know how bright it is. It can then be used as a standard candle to determine distances to objects such as other galaxies.
There are irregular variable stars which change in brightness in seemingly random fashion in a day, a month, or a year. But there are also stars that are predictable, varying in brightness regularly or periodically. This star, for example, called an RR Lyrae star, changes its brightness regularly in periods of several hours, year after year. Despite the fact that the RR Lyrae stars are several times larger than our own sun, they're regarded as small members of the family of regular variable stars. There are also larger periodic variable stars called Cepheids that change in brightness regularly in periods of days. Cepheids are about 100 times larger than our sun. The largest periodic variables in the sky are called Miras. These stars change in brightness regularly over periods of months. The cause of these changes in brightness is a physical pulsation, an alternate swelling and contraction in a rhythmic manner under the opposing forces of gravity and gas pressure, which are never quite in balance, as is in a normal star like the sun. This pulsation occurs over and over again for thousands and thousands of years. One of the most amazing properties of these regular variable stars is the beautifully simple relationship between intrinsic brightness and a period of pulsation. The larger, brighter stars have longer periods than the smaller, fainter stars. Because of this period luminosity law, it's possible to determine the intrinsic brightness of a pulsating star, which provides its distance from a simple knowledge of its period of pulsation. Because changes in the brightness of many variable stars are noticeable and measurable even with small telescopes, the observation of such stars is one area in which amateur astronomers have been able to make major contributions to astronomy.